This video I want to talk about motion. We'll consider a particle moving in a three-dimensional space. We'll characterize it as to the right from our point of view being the x direction. Back away from us is the y direction, that's into the page, and then z direction upward toward the ceiling. And we got some particle moving around in this three-dimensional space, and we can specify its position at some instant in time as by means of a position vector r1, and then suppose at a later instant in time it's at a different position vector r2, and what has gone on is in between from the time it was at position r1, let's say that occurred at t1 until the time it's at position r2, let's call that t2. It's changed its position by an amount we refer to as the displacement, delta r. So r1 is a position vector of the particle at time t1. r2 is another position vector, and delta r represents the change in the position vector that goes from the position it was at time t1 to the position it was at time t2. We see that we've got a vector addition triangle in three-dimensional space there, which is saying that vector r1 plus delta r is equal to r2. Now, I can look at this two ways. I'm saying the arrow says which way and the scalar here says how much, or I can say this arrow is a vector and the name of that vector is delta r, so I've actually used both labeling conventions in one graph. But we see that delta r itself can be expressed as r2 minus r1. I just have subtracted vector r1 from both sides. So in the Cartesian unit vector notation, r1 can be expressed as x1, y1, z1 times I, j, and k all added together. So more specifically, x1i plus y1j plus z1k. r2 can be expressed as x2i plus y2j plus z2k. And then their difference between them can be written simply as delta r is equal to, so this is coming down from this equal sign, just plug it into my expressions for the r2 and the r1, x2i plus y2j plus z2k. Then minus, same thing for vector 1, so delta r is x2 minus x1 times I plus y2 minus y1 times j plus z2 minus z1 times k. So there's a displacement vector from position 1, which I said was the position of the particle at time t1, to position 2, which I said was the position of the particle at time t2. We can write this as just delta r is delta x times I plus delta y times j plus delta z times k, where I'm simply defining x2 minus x1 to be delta x, etc. And then the average velocity from time t1 to time t2, that is from the time when the particle was at position given by a position vector r1 to the position corresponding to the position vector r2, I can say the average velocity is delta r divided by delta t. That we can write as delta xi plus delta yj plus delta zk. Let's make sure that looks like a j there. All with the hats on there divided by delta t. So that's the average. Go ahead and divide the delta t into each term individually. So that's delta x delta t times I plus delta y divided by delta t times j plus delta z divided by delta t times k. And we can call this change in the x component of the position divided by the amount of time it took to do that as the average as the component of the x component of the average velocity over that time interval from time t1 to time t2. So this I could call v x average times I plus vy average times j plus vz average times k. Now, if we take the limit as the time becomes smaller and smaller, as delta t becomes very, very small, so delta t, well, let's say t2, by the way, is equal to t1 plus delta t. That was just, I just defined that as t2 minus t1, so that's just a tautology there, just an obvious statement. But if we let delta t get smaller and smaller, t2 and t1 become very, very close together. And what happens, however, is as delta t becomes small, the change in the x position, the change in the y component, the change in the z component also become very small. And essentially, the 2 points are at the same position. R1 and R2 are very, 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 very close to each other, and we can refer to what was the average velocity, v itself, as the limit as delta t gets very, very small of the average velocity. And this would be, for the case that I've been talking about, it would be the velocity at position 1, so, and at t1, where t2 becomes very, very close to t1. So we can define an instantaneous velocity. Now, the thing is, what I've defined here is a way of calculating the instantaneous velocity, but the instantaneous velocity, you should know, is just how fast and which way the particle is going when it's at a particular point in time. So that's more or less, that's the regular velocity, what we call the instantaneous velocity. How fast and which way it's going at one instant in time is the velocity at that instant, the instantaneous velocity. It's the velocity that you're used to, the velocity that you get the magnitude of when you look at the speedometer of your car. It's telling you the magnitude of the instantaneous velocity, and then if you just look at which way your car is pointing, that's the direction at that instant. And even if you're going around a curve, your car is pointing in one particular direction at a given instant. So the two of them together, the speedometer reading at a particular instant in time and the direction in which your car is pointing at that particular instant in time, assuming that you're going forward, you're not skidding sideways, is your instantaneous velocity. So velocity and instantaneous velocity you can think of as just regular velocity. Imagine that we did that up here. So we found the velocity at this particular time, and then at some later time, a finite later time, not an itsy bitsy, but at a later time, we did the same thing. Found the position at that later time, and then just a little bit later, and in a very, very tiny amount of time after that, and we use the change in position starting at the later time, going to the even, but just a little bit later time than that, to get instantaneous velocity at one time, instantaneous velocity at another time, and I'll call those T1 and T2. So now I'm talking about instantaneous velocity rather than position at an instant. So we know the velocity when the particle is here, so it's got a velocity v1. So it's a magnitude and a direction, and then later on, let's say it's got a different velocity, v2. Maybe it's going a little bit faster, but in a slightly different direction. And again, we're in this xy coordinate system. So into the page was my y direction, to the right, the x direction, the z direction, this way. Out toward the frontier would actually be the minus y direction. And we can talk about the fact that the velocity from one time to a later time changes. Now I'm going to let this be a finite time for the moment, so not infinitesimal, not tiny, 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 but an actual finite amount of time. And we can use vector addition with these velocity vectors. So these points represent where the particle was at, but the velocity is just a magnitude and a direction. It's not a location. So I can put v1 here, v2 here. So I'm trying to copy these down without changing their orientation or their length. I think v2 looked a little bit more like that. So this would be the change in the velocity. This is just a vector addition diagram, more abstract than when we're talking about vector addition for positions, but we can still say the velocity at time 1 was equal to the x component of the velocity at time 1 times I plus vy1 times j plus v. I think I'd rather do the subscripts in the opposite order, so I'll go v1 x component, v1 y component, v1 z component, and then I got the I, the j, and the k. And then same thing for v2. And I can say the change in the velocity. Looking at this vector addition diagram, by the way, v1 is equal to, that's not what I wanted to write, v2 is equal to v1 plus delta v. So when you add two vectors, you put them head to tail. Here's the head of v1 to the tail of delta v. So it's these two that are adding up, and then the summation vector is the one that goes to the tail, from the tail of the first one all the way to the head of the second one. So this is this vector addition diagram, and if I solve that for delta v, I see delta v is v2 minus v1. You can think of that as final velocity minus initial velocity, which is the change in anything, the final value minus the initial. Here, of course, we're dealing with vectors. So let's go ahead and put this down. v2x times I plus v2y times j plus v2z times k. And then minus v1xi plus v2, not v1y times j plus v1z times k. K hat, of course. And so delta v is v2x minus v1x all times I plus v2y, same thing for the y's, times j plus v2z minus v1z all times k. So this is our delta v, and the delta v we can just write as delta v vector is equal to, this will be the change in the x component, v2, just call it delta vx times I plus delta vy times j plus delta vz times k. And the average acceleration from time t1 to time t2 would be the change in the velocity that occurs from time t1 to time t2 divided by t2 minus t1, which I'm calling delta t. So that'll just be delta vx. I'll just copy the whole thing down. That's times j, that times k, all divided by delta t. And I can distribute that delta t, that's delta vx over delta t plus delta vy over delta t. That's times an I there, there's a plus sign. That's times a j here. And then plus let's make that times a j there, and then plus delta vz delta t times a k hat. Alright, this is delta vx delta t times I plus delta vy over delta t times j plus delta vz over delta t times k. So A average, we can call that AX average times I plus AY average times J plus AZ average times k. Now the thing is, if we let delta t become very, very small, so we look for just a very short time interval after time 1, in the limit as delta t gets close to 0, the change in velocities, each component is going to be very small as well, and we can refer to that as the instantaneous velocity. So in limit as delta t goes to 0, it gets smaller and smaller and smaller, but it's still not quite 0, becomes infinitesimally small. A average just goes to the instantaneous, which is typically just referred to as A, the vector A. So at a particular instant in time, when this original particle is right here, it's got some velocity, which I call the instantaneous velocity. It's how fast and which way, and it's also got some acceleration when it's at that point, how fast and which way. And in this picture, what we've done is let this delta r shrink down to an infinitesimal to talk about the instantaneous velocities. And then we talked about a completely different position and a different velocity, and then let the time interval between those 2 points shrink down to 0. So we get this idea of instantaneous velocity, which is just your regular old velocity, how fast and which way something's going at an instant in time. But we've linked it to ways of calculating it, which is the idea of the displacement divided by the time interval. And to get the instantaneous values, we just let those shrink down to nothing. By the way, in calculus class, the way they write those, and I do want you to be familiar, like you don't have to be able to do derivatives, but I do want you to be able to read the equations as sentences. We say the velocity is the derivative of the position with respect to time. The notation is supposed to indicate that we're talking about a tiny change in position divided by a tiny change in time. The little d represents an infinitesimal change in something, whatever follows. No, that is not d times r. That's to be read dr, or the derivative of r, and then with respect to t. Our shorthand way of saying it is dr by dt, and then the longhand is the derivative of r with respect to t, or the derivative of the position vector with respect to time. And that's our instantaneous velocity. Our instantaneous acceleration is the derivative of the velocity vector with respect to time. Now I want to go back to look at all of these, and now that we've talked about position, velocity, and acceleration, all of them can be a function of time. I want to, and we've talked about it in the most general case. We've got some particle in space, in a three-dimensional space, moves from one position in that three-dimensional space to another, and we can talk about the displacement, the delta r, the change in velocity, the velocity, the change in position is the displacement, the change in velocity, and the acceleration. Make sure you never say acceleration is change in velocity. When there is acceleration, the velocity is changing, and the acceleration is how fast and which way the velocity is changing. So to get back to that before I move on to the next topic I already started, the velocity is how fast and which way the position is changing, and that's what this equation means, the derivative of position with respect to time. And it is, yes, always with respect to time. When something's changing, it's different at a point in time that's later than now, and that means it changes as time goes by, so it's changing with respect to time. And the acceleration is how fast the velocity is changing with respect to time. So if it changes a little bit in a second, we could say the acceleration is going to be small. If it changes a lot in a second, the acceleration is large. But we don't necessarily have to worry about a second. Just the unit of time. It's not a special amount of time. All right, but what I wanted to, what I was just starting to allude to before I decided to review that was, suppose that the motion is all occurring along the x-axis. So if we got a coordinate system, despite the fact that it's a three-dimensional coordinate system, we find our R1 corresponds to being out there, our R2 out there. Everything that's occurring, although it's occurring in a three-dimensional space, is occurring just along an axis. In that case, and we'll go through and modify this. So what I had was good for the general case, but now I want to look at the specific case. In that case, this is 0, this is 0, this is 0, this is 0. All of these are 0. So all the y's and the z's are 0 if it's sticking to the axis. Y represents how far away it is from the x-axis and this back into the page direction, and z represents how far it is from the x-axis and this back into the page direction. Z represents how far away from the x-axis we are in this up toward the top of the page direction. But if we're strictly on the x-axis, then both y and z are always going to be 0. And all this stuff just goes away. You know, the z goes way up there. All these pieces go away. all this goes away, that goes away. It's the same analysis for this special case. It's just that it's simpler. We would have had to write an awful lot less because, you know, y is not changing. It's just always 0. The z value is not changing. As far as our average is concerned, we'd have zeros for the y part, 0 for the z part, so we can just leave the whole thing off. And the time doesn't, we can't simplify anything with the time, but again, with the velocity, if it's strictly along the x-axis, it's never got any component of velocity that's not along the x-axis, so never got any component of velocity along the j direction or the k direction, so all this goes away. Up in here, these parts would go away. Over here, that means this all goes away. This would not be there. This would not be there. All we would have is this. So let's see if we've got everything now. Yeah, we'd have no acceleration. If there's never any velocity or change of velocity in the y or z direction, all that would be gone. And this down here, for the special case, particle always, and I guess I should have kept that in brown. That's what all that brown notation meant. Case particle always on x-axis. And for a train moving along a straight track, for instance, that's pretty normal. Or just something that's a swimmer swimming along a particular lane in a swimming pool. They just travel along a line, so you can divide that line, and perhaps the initial direction in which they're swimming is the plus x direction, and the person always stays along that line, always stays on the x-axis. So it's a very common situation, but birds, for instance, typically don't do that. We do get things do move around in three-dimensional space, so it's not the only possible case, but it is a pretty prevalent case and an important one. So in that case, our velocity would just be equal to dx by dt times I, and our acceleration would just be dvx by dt times I. We can, so our position vector, by the way, would just be r would always be equal to x times I, and as we write these equations involving the position, velocity, and acceleration, we see every single one of them, if the thing is constrained to move along the x-axis, is going to have this I in it. Everything is always going to have an I multiplied an I, and if we factor out the I, then we can talk about just the components without it. So we can talk about the x, the vx, and the a sub x. And in fact, this is for motion along one dimension. This is what we do, and quite often we leave off the subscript x and in both the velocity along the x direction and the acceleration along the x direction, in cases where we know, okay, we're just dealing with motion along a line. Now keep in mind, if the value of x is negative, when we were all the way up here, if the value of x is negative for for a given position, that means it's like we're over here someplace. Better not do that one in the brown, but we're over here someplace. And in fact, if all there is an x component, if we're talking about something that's along the x-axis, then it just means that we're to the left of the origin. So a negative value times I corresponds to a position vector that extends from the origin to a point on the negative part of the x-axis. And similarly, if the velocity x component is negative, so we got some number in here while we were working with the average velocity. If we had some negative number here, it just means it's got a component of the velocity in the negative x direction. And so we say that when we're dealing with just the x component of the velocity, because we're considering a particle that's constrained to move along the x-axis, we can characterize the direction by means of a plus or minus sign. So if x itself is negative, for instance, it means the particle is to the left of the origin, to the left of what we call the start line. If Vx is negative, it means the particle is moving leftward, in a case where we're calling rightward the positive direction. So I should make sure that that's clear. If I call, there's my x is equal to 0. Right there, this is my x-axis, so the positive x is to the right. If I'm over here, then x is negative. Over here, x is positive. No matter where the particle is, if its velocity is this way, then Vx is negative, whereas if its velocity is this way, Vx would be positive. No matter where the particle is, if it's the direction in which the velocity is changing is that way. So we got the acceleration itself as a rate of change of velocity. That's how fast the velocity is changing. If it's changing to the left, then a sub x would be negative, and if it's changing to the right, a sub x would be positive. By the way, if the particle is moving to the right and at an ever-increasing speed, then a sub x would be positive. A sub x is to the right. If the particle is moving to the right, but it's slowing down, then the acceleration is to the left. The direction in which the velocity is changing is leftward. If the particle is moving in the minus x direction and it's slowing down, then the change in velocity is to the right, and we would say the acceleration is positive. If it's going backwards and speeding up, so this is getting bigger and bigger, then the change in the velocity is negative. It's in the minus x direction, and the ongoing change is negative, so we got a negative acceleration. So a big part of this idea was to say, when we deal with just the one-dimensional case, we're dealing with just one component of the three-dimensional case. And we're able to avoid writing the IJK notation, even though the quantity, the velocity, the position vector, and the acceleration, they're all vectors. We can get by with just dealing with the numbers, which represent the scalar x component of the motion. Okay, that's the main thing I wanted to get to in this little video, so let's call that a wrap for our motion video.